Hello everyone, myself Dr. Priya Vashisht, working as an assistant professor in School of Chemistry and Biochemistry, Thapar Institute of Engineering and Technology, Patiala. I welcome you all to the series lecture of phase rule, and in this lecture we will be discussing the example of simple eutectic system, that is lead silver system. Simple eutectic system I discussed with you people in the previous video. Next we'll be taking up the process of desilverization of lead in Pattinson's process. The sequential outline of this lecture being the lead silver system as an example of simple eutectic system, and how this lead silver system can be applied, that is the phase diagram of lead silver system can be applied for the desilverization of lead in the Pattinson's process. So this is the phase diagram of lead silver system. Both the metals lead and silver are completely miscible in the liquid state and do not result in any compound formation. If you can recall from the previous video where I discussed simple eutectic system, the metals should be miscible completely in the liquid state and should not result in the compound formation. That is, both the metals lead and silver are completely suitable for forming the simple eutectic system. And as you can see from this phase diagram, it clearly resembles the phase diagram of simple eutectic system as I discussed in the previous video. Just the difference being that there we had specified an arbitrary metals A and B, but here it is the specific example is being taken, that is of lead and silver. This phase diagram is a TC diagram that are applicable for the two component systems, and as I discussed. On the leftmost side is the 100% lead, that is pure lead, and on the rightmost side is the 100% silver, that is pure silver. And this capital A point represents the melting point or freezing point of pure lead, that is at 327 degrees centigrade, while the point B, that is capital B, refers to the melting point or freezing point of pure silver, that is at 961 degree centigrade. There is a big difference between the melting points of both the metals. And as you can correlate this phase diagram to the diagram of simple eutectic systems, the meanings of the curves, the points is exactly same as we discussed there. No doubt I will be taking up the curves and the number of phases along the curve in areas and the calculation of degrees of freedom along in this diagram also, but that I'll be taking up later on as a revision. The main focus of this video will be how this lead silver system, phase diagram of this lead silver system is applied for the desilverization of lead in the Pattinson's process. So let's see how the process of desilverization actually takes place. Before we move to the process of desilverization, it's very important to be familiar with few terms. That is, what do we mean by argentiferous lead? Argentiferous lead is this lead that contains silver. That is, in a sample of lead, there is an impurity of silver present. That sample of lead containing silver as an impurity is known as argentiferous lead. Now, we want to remove this impurity silver from the lead sample to get the pure lead. So that process of separation of silver is known as desilverization. So the process of Pattinson's process for desilverization is named after the scientist Pattinson's. This is a very significant process used in the metallurgy, and this is the process regarding recovery of silver from the argentiferous lead, that we can remove the impurity silver to get the pure lead. The basis of the process is the phase diagram of the lead silver system, and in this process the impure sample of lead, that is argentiferous lead, that has a very small amount of silver, is heated and then cooled to get the pure lead, and the remaining liquid gets richer in silver. So the process is known as Pattinson's process. As we move further in the upcoming slides, things will be more clear to you how the process actually takes place. So coming to the process, as you can see from the phase diagram, pure lead melts at 327 degrees centigrade and pure silver melts at 961 degrees centigrade. Now for the process, the sample of argentiferous lead that has a very small percentage of silver, say about 0.1% of silver is present, it is heated to a temperature that is well above the melting point of pure lead, so that you have liquid melt wholly present now. Now say the point is represented by the point A. When you start cooling this liquid melt, then what are the observations? When we start cooling this liquid melt, temperature of the melt will fall along the line AB. Temperature will fall along the line AB. There will be no change in the composition of the liquid melt till the dotted curve AB is traced. That is, only we are lowering down the temperature of the liquid melt. Now, as we are cooling this liquid melt, as I mentioned in the previous video while discussing eutectic systems, what do you expect that when we are cooling this liquid melt, when we reach at this point, that is 327 degrees centigrade, pure lead should separate out as we have reached the melting point of lead or the freezing point of lead. But if you can recall, I had already explained to you that since this sample of lead is not pure, this is argentiferous lead and has silver as an impurity in it, so its freezing point or melting point will be lowered. Had it been pure silver, it would have solidified at 327 degrees centigrade. Now, when the cooling process is continued, at a point B, the solid leads start separating out. When at the point B, the solid lead has started separating out, the composition of the liquid melt that had lead and silver as an impurity in it, both in the form of liquid, that is the homogeneous melt of both the metals. Now the composition of that original melt has changed. In that original melt, we had 0.1% of silver, for example, and rest was the lead. Now since at point B, the solidification of lead has started, and now the composition will no longer be the same as we took for the original melt. Further cooling will shift the system along the line BC. This is B and C capital, that is, this will be the line traced. What does it mean? It means that once the solidification process of solid lead has started, the composition will keep on changing. And every time when the solid lead has separated, the further cooling will shift the line BC, will shift the curve towards BC, and the temperature will obviously lowered. As the more and more lead sample is being separated out and the composition of the liquid melt is changing, the graph, that is the curve, is shifting more towards the percentage of silver. That is, the percentage of silver is increasing. Lead is continuously separating out and it is removed. What do I mean? That the liquid melt is getting richer in silver until point C is reached. When the solid lead is being separated out and further cooling is taking place, since the composition of the liquid melt is changing, it is getting richer in silver. The relative amount of silver is being raised to 2.6% at this point, capital C. When we reach at this capital point C, solid silver also begins to separate out. And if you can recall, when the other metal also starts separating out at this point is known as eutectic point, and this corresponds to the temperature 303 degrees centigrade. You are very well familiar what do we mean by eutectic point, what do we mean by eutectic temperature. Now if I further cool the mixture of the composition corresponding to point C, silver and lead will separate out simultaneously. From these observations, what do we finally conclude? We conclude that solid lead can be separated out. The solid lead that is being separated out and removed continuously is in pure form now. It does not contain silver. This solid lead can be obtained only till the composition of the liquid melt has 2.6% of silver in it. Once the composition of the liquid melt has reached a stage when it has 2.6% of silver, that is at this point we cannot separate it anymore, because now at this point both the solids are being separated out simultaneously. Second very important point is the original argentiferous lead sample, which might have contained say 0.1% of the silver, which might have contained originally 0.1% of the silver, has now being enriched in silver, and the amount is being reached to 2.6% now. The curve is shifting towards the percentage of silver, and this is attained at point C, where the percentage is 2.6%. You have to be very specific about the percentage, because these are the experimental findings and verifications that this is the only point till when the pure lead can be separated out. This process of enriching the alloy in silver, that is the relative proportion of silver, is increased in the liquid melt. To what stage? To a stage when it has 2.6% of silver. This process is known as Pattinson's process. So this was how the process of desilverization takes place, and what do we mean by Pattinson's process. You should be very clear about the definitions also. Now, taking a recap of the lead silver system as an example of simple eutectic system, AC represents the freezing point curve of lead, that is, it represents variation of melting point of lead on addition of silver. And how does it happen? I have already discussed it with you. Along the curve AC, solid lead and solution, which solution? That is liquid melt of both the metals, coexist, that is number of phases is equal to 2. And this is a two-component system, hence applying reduced phase rule. You are even familiar now. Why are we applying reduced phase rule? It comes out to be a univariant system. Same implements for the area ACE, that is there are two phases in it and the system is univariant. On the similar lines, the curve BC is the freezing point curve of silver. That is, it represents variation of melting point of silver on the addition of lead. Along the curve BC again, solid silver and solution of what? Liquid melt of both the metals, that is silver and lead, they coexist. Number of phases again rising to 2. So this is a two-component system. Reduced phase rule applies and the system is univariant. As I explained you that how this curve AC is traced, that liquid melt is melted, and how we get the finally we get the solidified lead and the point C is reached, similar explanation can be done for obtaining solid silver also. Along this area, in this area BCF, again two phases coexist and the system is univariant. So if you can recall the naming of the curves, the significance of the curves, the information conveyed from the curves and areas is exactly the same as we did for the simple eutectic system. And below this we get solid silver plus eutectic, solid lead and plus eutectic. So what is this eutectic point C? This is an invariant point. Why this is an invariant point? Because the three phases, that is solid lead, solid silver and their liquid solution coexist, and when we put all these values, that is P is equal to 3 in reduced phase rule, we get degrees of freedom to be 0. The system is univariant, that is, it is well defined. There's only one temperature that corresponds to eutectic point, that is 303 degrees centigrade. And what is the composition of eutectic at that point? It's 2.6% silver and 97.4% lead. So these values of temperature and composition at eutectic point are very, very important. And so this is how do we actually achieve the process of desilverization, applying the system of desilverization. Thank you.